Welcome to Quantum Software Talks. We'll just we'll pretend that I didn't do this already. But yeah, the series here where we find and feature really cool open source, quantum open source projects and maintainers. So I'm super excited to be here with Pedro today, who's actually one of our Unitary Fund micro grantees. So yeah, I'm super excited. What can I say? I am super excited to be here chatting with you today, and yeah, for folks to learn more about QRAND. So maybe you can tell us just a little bit about yourself before we get into learning about the project.
Sure, of course. So as you mentioned, my name is Pedro Rivero. I just finished my PhD in physics at Illinois Institute of Technology, where I've also been doing research alongside Argonne National Lab in finding algorithmic ways of simulating nuclear physics on quantum computers. Kind of as a side project, while I was doing the PhD, I wanted to develop QRAND, which is, as Sarah mentioned, is a tool for generating quantum random numbers in several different ways, as you will see soon in the talk. And yeah, I mean, really appreciate Unitary Fund having me here, and super thrilled to be able to share this with you.
And for clarity, Pedro finished his PhD like a couple weeks ago, so like congrats again. That is that's a lot of stress to just kind of be done with. So yeah, here let's take a look at your slides. Hopefully everybody can see them, and I'll let you take it away.
Right, thank you so much, and I see people are congratulating in the chat, so thanks a lot. So. Again, I'm going to present QRAND, which is a multi-protocol and multi-platform quantum random number generation framework. And so for this, this is the topics that I will be covering today. I'm going to start by talking a little bit about the state of the art, kind of why random numbers are important, what do we mean by random, and how can we actually generate random numbers. This will help us contextualize all the work. Then I will start talking about how can we actually generate random numbers using quantum computers. And I will talk about 4 different protocols, 2 of them which are implemented currently in QRAND, another one which we are looking forward to implement, patent permitting, which is kind of what we're looking into now, and another one which is kind of like farther down in the future, because we still don't have the quantum computers to be able to implement this, but which is nice and kind of showcases why this is a super useful tool. And then I will be talking about QRAND, how it's been developed, kind of what its structure is, and what you can do with it. So let's get started. So first of all, why do we need random numbers, right? So actually, there are quite a few applications for random numbers. First of all, they're crucial for information and communication security. We need them for crypto systems, Internet of Things, which is becoming a great thing these days. We can also use them for computation. There are several algorithms which are basically based on randomness procedures, like Monte Carlo methods. Physical simulations are also done through random numbers in several cases. We also need them for financial systems to make sure that transactions are secure, that our credit card chips work fine. And we can also use them for statistical sampling or testing, as in randomized benchmarking, and of course for legal or trust-sensitive processes like jury choosing, lotteries, and so on and so forth. By the way, what we mean by random numbers is not that the numbers are random themselves, but that they are randomly generated, which is an important distinction to make, as we will see. All right. Is this working?
Yep, you're all good.
Okay. So what do we mean by random? So this actually turns out to be quite a slippery concept. The attribute of being random, as I just mentioned, is applied more correctly not to numbers, but to sequences of numbers. And it is strictly related to the lack or impossibility of predicting what the next number or the previous numbers were. Actually, there is a nice mathematical definition of randomness provided by Kolmogorov, which actually states that randomness is the impossibility of compression, for those of you who are familiar with these kinds of tools in computer science. So let me actually, to understand what randomness is and how we're going to measure, we will be using Shannon's entropy, which is a measure of uncertainty or disinformation, and can be, in very simple terms, understood as the minimum number of yes/no questions that need to be answered about something to be able to guess it correctly with 100% confidence. Again, let me remark that bit strings are not random. And so when we take a look at them, we will actually see that in certain cases, if this bit string is not perfectly randomly produced, we'll see that the randomness of that bit string is actually has fewer bits than the length of the string itself. All right, so we actually see that. Sarah, can you check that the screen is mirroring correctly? Because I don't know why I see full green on my screen, and I don't know if that's a problem.
It's on the randomness quality slide.
Yes.
Mm-hmm.
All right, cool.
I did have a quick question though. So how does, if a bit string is not necessarily like as random as like a choice per bit, how does that work with one-time pad encryption?
So how does that work with one-time pad encryption? So
my naive assumption was then that like that was the full description of, if you could compress that, then that seems to break how that works.
So it's kind of different when we talk about one-time pads and when we talk about the randomness generation. So in one-time pads, you essentially have a small amount of entropy. I will talk about this a little bit later, but what you actually have is a random sequence, and from that random sequence, you're expanding its entropy into like different chains of bits. The issue with that is if I got to know that initial seed of entropy, I could perfectly predict all of your one-time passwords. So that's kind of one of the biggest problems of classically generating random numbers. I will touch upon that a little bit later, but that's actually a great question.
Sorry for jumping the gun on that, but I always this has always been something that's kind of confused me about like how do you actually measure randomness and stuff. So I'll stop interrupting.
No, that's fine. So you essentially just need to, you can just use the definition that I just gave, which is just try to count how many yes or no questions do you need to be able to guess the string perfectly, right? So if you have 2 questions for that, then it's a 2-bit entropy for whatever you have. It can be like a huge sentence, or it can just be like 2 bits. But yeah, that's how you measure randomness and entropy, basically. All right. So coming back to this, the problem with all these procedures is that it is nearly impossible to establish whether a source of entropy is truly random or not. And so the best we can actually do is just analyze the outputs of that source for statistical properties, such as like its weight, or just how often it produces certain patterns and things like that. But again, the problem with that this introduces is that a passing output will always pass the tests. So I can perfectly, me or an adversary could fabricate that random number and just send it to you as if it was perfectly secure and random. There's actually to illustrate this, there's a book on Amazon that you can look into it. Comments are fantastic. That it's 1,000,000 random digits. And so you can actually see in the comments that people are saying things like, I bought 2 copies of this book and I find that the first copy perfectly predicts what the numbers are in the second copy. I feel cheated. And this actually explains what I mean by the fact that numbers are not random themselves. It's just the way we produce them. In this case, since this guy was producing the numbers through the exact copy of the book, there was no unpredictability, and so the randomness was essentially 0. All right, so what properties do we need to generate good random numbers? So first of all, we need uniformity. We want all sequences to have kind of the same probability of occurring. We need scalability, meaning that if a test that we're doing to check if the entropy is acceptable is applicable to a sequence, it also has to be applicable to any subsequence in a kind of recursive way. This is a very strong assumption, and it makes checking for randomness very, very difficult because it's exponentially time consuming. We also want it to be consistent, meaning that the behavior must be the same across all different outputs. And then we have forward unpredictability, which is something that we all, it's kind of intuitive to us all. If I have the one of these random outputs, I cannot predict what the next random output is going to be. And then backward unpredictability, which is not so intuitive to us, but it's also very important for security. And it means that if I have one random number, I cannot predict the numbers that came before. In other ways, if I find out what your password for LinkedIn is, I cannot find your password for Skype that was generated before, right? So these are all very important properties that we will accomplish by using quantum computers. So just the general landscape, and this again comes to the question that Sarah asked before. These are the different ways that we actually have for generating random numbers. First of all, we have what are called pseudo-random numbers. These are deterministic algorithms that come with what we call a random seed. You can actually see here that this protocol, what this figure is representing, is not actually generating random numbers, but expanding the entropy. It means that we start with a small sequence of allegedly random bits, and we pass those through a classical algorithm that produces a much larger sequence of seemingly random bits. And this is how the one-time pad works, right? So we do have stored in our phone or our laptop a small sequence of supposed to be random bits, and through an algorithm we produce all the different one-time pads. But if someone were to guess our initial seed, then they will be able to reproduce all of our one-time pads. All right. Also, as pseudo-random number generators, we have the so-called cryptographically secure pseudo-random number generators, but these, in many cases, are thought to be not really possible theoretically, and so it's kind of an open question right now if we should be using this for secure purposes or not. Although we do, because we don't know of good ways to break them, but theoretically they could be broken. And then we move to true random number generators. These don't rely on deterministic algorithms. Instead, they are based on either physical or non-physical processes. Non-physical processes are, for instance, measuring how fast you type on your keyboard, and through that, through those bits, you can actually produce some randomness. Those are not fully reliable because, again, you can imagine that when you're typing on your laptop, you might have some patterns in the way you type, and so those patterns can actually be reflected or mirrored in your random sequence, and so you're effectively losing randomness through that. And then we have true random number generators based on physical processes. And once again, we have to distinguish between classical true random number generators, which are mostly based on chaos theory, but they are ultimately deterministic, so they are not as secure as they could be. And finally, quantum true random number generators, which is what we will be using, and they exploit the quantum mechanical property of superposition and the collapse of a wave function to actually produce true randomness. So this is why quantum computers are very useful for these purposes. So let me just go for it.
There is a quick question from chat, which is if somebody asks you to choose a random number, we as humans, are we actually picking truly random things, or where do we fit in that diagram?
So that's actually a very good question. And so what I've actually seen is that we actually have some kind of bias, because subconsciously we are influenced by kind of the things that we perceive in kind of the place where we are, right? So I actually saw some magic tricks. This is kind of departing from the talk, but I saw some magic tricks where magicians actually were kind of trying to induce you to choose a particular number by either like showing you like 3 with their hands, and so that kind of predisposes you to actually choose that number. So we are not really completely random ourselves. We have a bias, and people can actually know how to exploit that. We tend to choose, say, for passwords, you can imagine people actually tend to choose their birth dates, which is not very secure, but for some reason we tend to do that. And if we're choosing, we have kind of subconscious biases. Yeah, that's kind of what I mean. Is that good enough answer?
Yeah, I think so.
Right.
Folks in chat are like, oh, questioning free will already.
Yeah, it's you know, messy stuff, but all right. So let's see how can we actually use a quantum computer to produce random numbers. So what you're seeing on screen is just the naive approach to producing random numbers, right? Let's first take a look at the left-hand side of the screen, where we just see, you know, a 1 qubit where we're using a Hadamard gate to prepare this superposition, like an equal superposition of 0 and 1, and then we measure, right? So sometimes 50% of the times that you measure these, you're going to get a 0, and the other 50% of the times you're going to get a 1. So there you go. There we have a random bit, a perfectly random bit, using the laws of quantum mechanics. And of course, we can just expand this and use several qubits instead of just one. And in that case, we will be getting, you know, strings of in the case of the right-hand side figure, 4 bits of or n bits of entropy, completely random. All right. This is the naive approach, though, and it has several problems. Most of them coming from the fact that this process is not perfectly reproducible. We have some noise in our quantum computers, and that's going to make some results more likely. So we would like to see how can we address this and make it even better. And a good approach to this is what we at QRAND, by the way, this protocol, which is the naive protocol, we just call it the Hadamard protocol in QRAND, and it's implemented like that. And if you refer to Hadamard protocol, this is what we're talking about. Another good protocol, as I was saying, is the entanglement protocol. This was proposed in a paper by Jakak and Jakak, actually, in Nature. And so what they were doing here actually was using entanglement to be able to, first of all, clean of any noise your randomness results, and second of all, being able to validate your output in a secure way through external means. So how does this work? You will understand it soon enough. So we see here that we have 3 qubits, but instead of having all possible 3 qubit sequences, we have this kind of entangled state where we see that these are all the possible sequences with even parity, meaning that if you count the number of ones, you're always going to get an even number of ones. This is, of course, just 2 bits of entropy, where we could, in principle, get 3. So you see how, in order to implement these techniques, we're kind of giving away some of the entropy, but we hope that this is actually going to be useful, and it will, as you will see. You see down in the left corner of the screen, you see this quantum circuit that actually prepares this state, and then we just take some measurements, and you see there's some sample measurements of what we could get, and we do see that the last bit here, the one that I'm remarking, this is just a parity bit, right? So we could actually use those results to be able to essentially get rid of all the output, which is not correct. So for instance, if we were to get here a 1 and then a 1 and a 1, this output here would be bad, and we would know that something funny happened in our quantum computer, and so we could just remove that completely. So that way would be purifying our entropy, and we'll be getting something more secure in a sense. All right. That's basically what I'm saying over here. As you can see, this is just the parity bits. And yeah, again, we can use it to purify it. And the nice thing about this is that whereas before we were doing it for 3 qubits, we can actually expand it to do it with as many qubits as we like. And in general, we will have one parity qubit that we will need to discard because it kind of relates everything else and it's predictable. we use it for purifying, but it has to be discarded. It cannot be counted as entropy. And then we have, actually, in this case, k sequences, which are okay. So the nice thing about this is that now, because of the entanglement in the procedure that we use, we know that every single sequence here, so this sequence, as well as this sequence, as well as this sequence, is going to have the same statistical properties, right? So we could just take one of those sequences, as we are showing here, and send it to an external source to validate it. Why would you like to send it to an external source? Well, basically because these sequences are huge, and sometimes we might not have the capabilities in our laptops to just validate these sequences, because like the time that it takes is exponentially growing with the size of your sequences. So generally speaking, we are not going to be able to perform as many validations as we would like. So a good way would be to just send it over the internet to some external source. They will validate it for you, and they will say, hey, this entropy is great. And so that way we'll be able to know that the rest of the sequences, the k-1 sequences, have good entropy, are completely secure because they cannot be guessed since we destroyed the parity bit. And yeah, so this is how the entanglement protocol works. Any questions to this point?
Charmer Dark was asking, and I think you had this on your previous slide, isn't noise random too? So that would be a good source as well.
It is, but noise is usually biased as well. Like we could use noise, but we need to establish what the properties of that noise are, because there might be certain bias towards, so in this case, noise could be thought of as we're producing more ones than zeros, right? So if we just use that noise, we would be getting something which is leaning towards the ones. And so even though it's kind of random and unpredictable, it's not as random as we would like. So if we kind of get rid of that noise, what we're doing is making sure that what we have is purely random. It has as many bits of entropy as can possibly have.
Makes sense. I've seen
right.
physical sources that just even the temperature, like, of the room that they're in can add some of those biases. So it can come from strange places, but yeah.
Yep. So essentially, what we'd like to know is that our process is perfect. It's producing entropy perfectly, and so noise, by definition, is something that we cannot predict. So I don't think we can actually say that our production is perfect if we are relying on noise, because we don't really know how noise behaves. All right, so this is all great, but the next question is, can we actually verify that we are not being fed all these solutions, all these random numbers by an adversary? And the answer to this question is actually yes. With quantum computers, there are ways of actually proving that the output that you receive, that the random strings that you receive, are truly coming from a quantum process, and they are not being provided by someone trying to trick you and fool you into using something that they already know as a password, for instance. There are several ways for this. One of them is one approach relies on having actually entanglement through like different devices, quantum devices, which you might imagine is not very efficient, because this means having actually several different machines entangled between each other, and I'm not sure that we can do this effectively yet. So even though it's theoretically nice, we would like to have something even better. And there's actually a way to do this using post-quantum crypto and other techniques, where we actually are just challenging the quantum computer. The quantum computer is giving you a response which you can actually interpret as your random answer, and from that random answer we come up with the next challenge, and the quantum computer answers again. And so by comparing the consecutive answers from the quantum computer, we can actually, and there are ways I'll show you later, we can actually prove that the output was truly generated by a quantum machine and not by an adversary. A way to do this, for instance, is what we call in QRAND the Sycamore protocol. This is something that we have not implemented yet because we are still looking into the patent that this algorithm has to see if we can actually, well, implement it altogether. And the way it works is essentially as follows. First of all, we need to have some seed. So again, this is going to be a random expansion protocol. And with that seed, what we're going to produce is a random quantum circuit. Next, what we're going to do is just perform a small number of measurements on these quantum circuits, and that's going to give us our randomness. All right, so how can we do now to verify that this was produced on a quantum computer? What we do next is simulate that quantum circuit classically, and this is very hard to do. So the point here is that simulating these results classically with the random circuit that you provided is exponentially hard. So a classical machine would not be able to do it fast. So if, a couple days later, you see that the results that come from that simulation match the results that you got, then you can just assume that that was done by a quantum computer because a classical machine cannot do it fast enough. And so if the results that you got took seconds and the simulation took days, then, well, it had to be done through a quantum computer. This protocol, by the way, was proposed by Professor Scott Aronson, and it is actually what was used by Google for his quantum supremacy claim a couple of years ago, which they did through the Sycamore quantum chip, which is what kind of gives the name to this protocol that we put together. All right. And next, we have the BCMVV protocol. This is based on post-quantum cryptography, and it's even better than the previous one because, as you noticed, well, if we wanted to essentially validate or verify that the calculation or the generation was done through a quantum computer, we had to wait like a couple of days for the classical simulation to finish, which is, of course, not very convenient. So how does this protocol work? This actually takes polynomial time, so this is actually very, very fast, and it works the following way. It's based on these challenges things that I was talking about before. So every step in the algorithm has 2 rounds. First of all, we propose a problem, and the quantum computer responds with an answer. That answer is going to be our random number. And then based on that random number, we're going to propose a challenge to the quantum computer. And the good thing is that we're going to be using post-quantum cryptography techniques to make sure that only a quantum computer can answer that challenge that we're proposing. So only if the quantum computer is holding some kind of quantum token, it's going to be able to answer.
So you're like the quest giver.
Yeah.
For the quantum computer.
Essentially. So here we have a small diagram of what this protocol would look like. First of all, we begin by just having 2 registers, and on the first register, we prepare a superposition of all possible states with that with that length, right? So then qubit register, so all possible bit strings of length n. Then our classical computer provides a problem in the form of a trapdoor clock-free function, which is a special kind of function used in post-quantum cryptography. And what you need to understand about this is that it's a 2-to-1 function. Okay, so we have every output is associated to 2 different inputs. Okay, and so those outputs, once you pass this through the quantum circuit, are encoded in the second register, as you can see over here. And so now all we have to do is just measure that second register, and that is actually going to give us our random sequence of bits. But the nice thing now is that once we perform that measurement, because there's an entanglement between the 2 registers, the first register where we were holding all the possible inputs is going to collapse into a superposition of the two possible inputs that give you the output that you measure, based on the trapdoor clock-free function. And so now the classical computer can actually challenge the quantum processor, and only if that superposition is prepared, so only if we actually have access to this quantum state, we're going to be able to answer the challenge successfully. And that's how we actually prove that the process was carried through a quantum device. The problem with this protocol is that it actually, so if you want to perform that connection to send the challenge, that takes you at least about 40 milliseconds when you actually measure the latency of sending information through the internet. And right now, coherence times in quantum processors are about 50 microseconds. So we're still a few orders of magnitude away from being able to do this. But once it arrives, it's gonna be revolutionary, I think. And we are preparing QRAND to be able to support this. All right, so that's it for the background. And now I wanted to move to kind of show you how QRAND is structured. This might be a good moment for questions if anyone has some. All right. Yeah, I know. I can actually. Oh, there you go. Yeah, I can actually zoom in.
Oh, sweet. Sorry. I the Donis. Sorry for the username. So in order to get a sequence of n random numbers, you just have to run the entangled circuit n times, right?
Let me go back to the entanglement circuit. So not really quite, because as you can see here, we're actually producing k-1 usable sequences. That means that over here, let me actually use a different color. So over here, we have k+1. We have to destroy one for the parity check, and we're using the other one for validation. So we are left with k-1 bits. So if we wanted to find what were you saying, n? So we would need to have n divided by k-1 times. This is how many times we will need to run it to get a sequence of that length. Because every time you perform a measurement, you're getting k-1 bits, essentially. Does that make sense?
Yeah, I think so. Good question, though.
Yeah, that was really good. Okay, so let me go back to showing you how QRAND works. All right, so what we wanted to do with QRAND actually was to be able to implement this framework that allowed you to have on one side different protocols and actually a way of coding new protocols if we needed to, and on the other side having different platforms that we could use for the generation of random numbers. So how do we do this? Okay, so let me start with the platforms. What we implemented in QRAND is, first of all, a class that's the quantum platform class, and this actually implements another different class, which is a quantum factory. And through this quantum factory, we are actually allowed to create quantum circuits, quantum jobs, and quantum backends. So how do we use this? Okay, so this actually what it's doing is providing a common API for all the different platforms that are out there. So for instance, we can actually have a qiskit platform that allows us to create qiskit circuits, qiskit jobs, and qiskit backends. But we can also have a qsharp platform that allows us to create qsharp circuits, qsharp jobs, and qsharp backends. And the same for cirq or any other given platform that you'd like. As of today, we only have implemented qiskit and qsharp, and we're working on cirq. So yeah, stay tuned for that. So what do we do next? Okay, so once we have a platform, we also need a protocol, right? And here's how we implement the protocol. We have an abstract class or an interface, that's the quantum protocol, and also another abstract class, which is the protocol result. And that's actually giving us both a bit string, which is kind of the output that we're looking for, and a validation token. And that validation token, for instance, in the entanglement protocol, is the sequence that we were saving for validation, right? So that's perfectly secure to send over somewhere else, and they're not going to be able to predict what your bit string is from that. All right. But we wanted to make this a little bit more versatile, right? So we have the quantum protocol, and that quantum protocol actually is implemented into this bare quantum protocol subclass, which gives us the Hadamard protocol, the entanglement protocol, the sycamore protocol, and so on and so forth, right? And this is great, but what happens if we wanted to add, for instance, validation, right? So what we did was we made this this quantum protocol interface so that it actually allowed to be able to layer in different validation techniques in such a way that we could start with just with the Hadamard protocol and then wrap it around with a validation decorator, right? And so this way, when we perform the protocol, it gives you the random numbers, and as it's coming back out, it's checking if those outputs meet certain validation criteria that can be established, say, by NIST, for instance. And we actually provide some of these validation techniques that NIST is encouraging people to use for random number generation. And you can see that over here on the right-hand side of the slide. What we essentially do is we have this bare quantum protocol. We pass it along to this validation decorator, and that validation decorator actually has different validation strategies in it. And that's what allows us to build or to customize the protocol that we want to use. We can just have a base protocol, say the entanglement protocol, and then we can add, so for my particular purpose, I want to validate it in this and that other way, because that's what's important for me, right? So this is allowed by QRAND. And the nicest thing is that we only need to implement the protocols once, because by using the common API for the different platforms, right here, if we use this common API for the different platforms to program these protocols, then I can, with just one program, I can run it on qsharp, I can run it on qiskit, I can run it on cirq, and so on and so forth. So this is the major idea behind QRAND. I don't know if someone has questions about this. All right, I'll keep moving, and if something comes up, just let me know. All right, so how does QRAND works? Okay, so first of all, it's, as I have already explained, it's multi-protocol, so we can actually have Hadamard, entanglement, sycamore. You can also, if you want, you can also code your own protocols. So you can use QRAND to write down protocols that then people can use on whatever platform they prefer, and with whatever validation technique they want. It's, as I have already mentioned, multi-platform. It also allows you to have different output formats. So you can output bit strings, ints, floats, complex number, hexadecimal, base 64, and a huge number of things. It includes an entropy validation suite. And furthermore, and I will show you this now, let me actually show an example with code. All right, so this is how we use QRAND, okay? We first import the quantum random number generator class, and then we need to import a platform and a protocol. In this case, we're using the qiskit platform and the Hadamard protocol. All right. So what we do is we instantiate the qiskit platform, we instantiate the Hadamard protocol, and we use those to build a quantum random number generator object. Okay. And from there, it's just as easy as doing get random bit string, pass on the number of bits that you want, and it gives you what you're asking for. But you can say get random int, get random complex polar, and you pass in different parameters. In this case, when you pass 1 and 3 and pi, essentially, it's giving you a random number which lays in the complex plane in the kind of like the upper half of the unit circle. But you can say things like get random base 32, and that will give you a string of base 32 characters with, in this case, 1000 bits of entropy. Now, what we might ask ourselves is, this is nice, but all the outputs that we're getting right here are uniformly distributed, which is great for certain purposes, but other problems actually require you to have different probability distributions, right? So what we did on top of all that I have already discussed is we added support for a NumPy interface. And what this means is that we can just use this quantum random number generator object, pass it into a NumPy generator, and start using it to generate different results according to like a normal distribution, a logistic distribution, a Poisson distribution. And we're doing this through, again, quantum computers. Why are we doing it through quantum computers? You can see that in this first line over here. Let me actually choose a different color. Because we're, in this case, I'm using the IBM Q platform to get the provider. And so internally, this is all handled by QRAND, and it allows you to query the different quantum backends to get the randomness that you need. And in this process of actually querying the backends, we perform what I call the efficiency sampling method. Now, you might imagine that, say you want 2 bits of entropy, right? And you ask the quantum backend for those 2 bits, and then you retrieve them. Okay, that might take, I don't know, depending on how busy the backend is, say 1 minute, 2 minutes, whatever. Now you need to another 4 bits. So you ask again, and you wait another 2 minutes. This is very inefficient, as you might imagine. So what we do is when you have not asked for any bits before, what you do is we query the backend and retrieve as many random bits as possible. Then we store those locally in memory, and every time that you're asked for new bits of entropy next, instead of querying the backend, we're just going to be using that repository of bits that we got from just one query. This makes the whole process much faster because we only need to connect once to the backend. And this is, again, all done internally by QRAND. You don't need to take care of this at all. It's just a nice thing to have to be able to produce as many random bits as you need in the smallest amount of time possible. And with that, I end my presentation. These are some references that I used both for the development of QRAND and for the presentation that I just gave. And if you have any questions, I'll be happy to answer them.
I'll do some here. I'll also bring myself back so you can see while we're talking. Yeah, thanks so much for giving us a great overview. I think this really helped answer some questions that I had about random things because it always is a bit confusing how like the how you measure and how you do the quality stuff, like, because it just seems like, well, if I measure them and it's like equally 50-50, then that should be good, right?
That could be, but not really. Yeah, so that's
Exactly.
why we're adding these validation things so that we can perform different tests. Mm-hmm. One of them is the 50-50 test, of course.
Yeah. But so got a couple questions. One from Charmer Dark, which I think you were touching on just in the last code samples, but how are the distributions generated? The protocol would just give out random bit strings, right? So that's NumPy,
correct.
Right?
Yes, that's correct. Yeah. So we use these protocols and all the framework that we have developed to produce uniform distributions, which is, by the way, what we know how to do with quantum computers, because apparently there are exponential overheads if you try to produce other kind of distributions. So yeah, we essentially produce uniform distributions and then feed those into NumPy. And NumPy is the one that takes care of converting those uniform distributions into something else, which is, again, it's don't reinvent the wheel. It's already done. So
It's out of scope. That's how you.
yeah.
Wrathful Spatula says passes the Die Harder test. um, but Andrea asks, you already mentioned something at the beginning, but can you explain a bit more about what the possible applications of this are? So like maybe a bit more about kind of the workflow where you'd expect somebody to be using QRAND.
Sure. I mean, it really depends on the application that you want. Like, again, you might be using it. For instance, there's a funny story that I have. Once that I attended a student conference a few years ago, and they were presenting these results on actually some simulations of fluid mechanics, which are very, very hard to do, right? So they took massive amount of time, like thousands and thousands, millions of nodes to actually reproduce it. And when you saw the results, you actually could see a pattern in the results. And so they were kind of like, look, this is amazing. We have found this pattern in something that's supposed to be turbulent. And when we started inspecting what was happening is that through this random number generation technique that they were using, that's what was introducing the pattern and not the actual simulation, right? They were simulating turbulence. And because you need to add some randomness to that turbulence, they got burned, essentially. So in that case, a good thing that you could use QRAND for is just start querying the quantum backend, okay? You leave it querying for a couple of days, and you build this massive repository of randomness. And then you can basically just use that for your, in this case, this fluid mechanics simulation, so that you don't reproduce these patterns. That would be one case. Another case would be you want to just have secure random passwords, right? You can query the quantum backend, build your repository of random bits, and then every time that you want to, you have to keep secure that repository, so just don't put it online. But you can keep that secure, and every time you need to get a new password, just say, hey, give me a random base 64 string, right? And that gives you a nice little password for you to use in no time. So that's, again, it really depends on the application that you want to pursue. But that's, again, random numbers are, as I said at the beginning, they're everywhere. They're used for anything that you'd like. You could use it also for algorithms and so on and so forth. But,
yeah, I guess like you kind of mentioned the deterministic algorithms that take a random seed that kind of do key expansion or something like that. So that's can be a helpful way to go about that.
Also, yeah, because if you think about it, we're always assuming that the seed is truly random, but we don't know that. So we could actually use it just to generate those seeds, and it could be a great use.
Yeah, that's kind of the root of your trust chain. if it's poisoned or corrupted from the very root, then you can't trust anything else. So, yeah. The Adonis asks, so you get only random bits, or can you get random integer numbers in a range?
Good question. That's actually a great question. So what we get from the backend are random bits, but we have implemented functionality to transform those bits into, as you said, integers within a range, or let me actually show you that. Where is it? Okay, right here. There you go. So as you can see, I can say, just give me a random bit string, or I can also say, give me a random integer with, 4 bits. Or I could say, give me a complex number that, lays here. I also have like implemented things like give me a float between in this interval, give me an integer in this interval. So yeah, you can produce anything you want, but what's being produced at the very basic level is bits, yeah, from the quantum processor.
Yeah, and they're also asking like with mod, so yeah, like I feel like anything you can do there with like NumPy, you can make happen, right?
Yeah, yeah, and yeah, with mod as well. Yeah, you can do whatever you want, and the nice thing is that it's done in a way that you're not wasting bits because you have them all stored. You just take the bits that you need for what you want to produce, and that's it.
Sweet. Yeah, and please, folks, put any other questions you have in chat. So I have we've got a few minutes here. I've got a couple questions for you though, which are, so the first is, what kind of got you interested in quantum computing stuff? Like, was it a course, and then like, you know, what drew you to randomness?
Those are actually very good questions. So I actually come from an engineering background. So my undergrad and master's was in aerospace engineering. So when I moved to physics, I was kind of looking for something that kind of was halfway through so that I could actually use my previous knowledge. And when I found about, it was actually on a class project that we needed to just explore a different field. And I found out about quantum computing. I thought it was terrific, and I just fell in love with it. Later on I just attended a conference at Argonne National Lab where they were talking about how we use quantum computers to simulate physics, and that's what got me into the PhD, and and so on and so forth. So and how did I get interested in random numbers? So it's actually based on that student conference when I saw that huge mistake, which was, again, no one could predict it. Like it's the last place where you would actually think an error is coming from. I said, hey, we need to address this, right? And with all the concerns that we have right now in terms of security and producing passwords and privacy and all these, I just thought, why don't we use this? We can use it with the technology that we have for producing secure random numbers. Let's go for it. This hasn't been done so far, so.
That's cool. A follow-up then. So you obviously, having just completed your PhD, know a lot more than when you started, hopefully. What, if someone was like a student just kind of getting started in quantum computing or maybe quantum software development, what one thing or skill or topic do you wish like you knew at that point? Like,
Question.
Like for me, I think knowing, like having better like software development skills and like knowing how Git worked, it would have made like some of my early homeworks, LaTeX, everything a lot easier.
I agree. Yeah. So I definitely, if you're interested in like quantum software development, I would say learn Git and learn design patterns, because design patterns help a lot in development. They make your code much more versatile, easy to use, compatible, understandable by the users, which is ultimately your goal. I guess you want to build something that can be used. So yeah, learn Git and learn design patterns. That would be my advice for young quantum software developers. By the way, I wanted to address this. All that I've been talking about in this talk is for QRAND version 1. Right now, what's published on PyPy is, I think it's version 0.4, if I'm correct. This version 1 is coming along before the end of the year. It's very similar to what's out there so far. It just changes in a couple of simplifications. But just wanted to make you sure in case you go and try to, get this the QRNG class and it doesn't work. It's because of that.
We're getting bleeding edge sorts of
yep.
sneak preview sorts of details here.
Essentially.
I'll give one more chance for folks to ask questions here. Someone asks, is nature fundamentally random?
I guess it is to some extent, right? Depends on your interpretation of quantum mechanics, which is open for debate.
That will be another talk. Quantum foundations
Yep.
is a whole nother can of worms.
No, but evolution is unitary. That was a good answer.
Way to go, Dan. Yeah, well, I think we're probably about on time to wrap up here. One other last question for you then. So say someone has watched this and is like super excited to use and or contribute to QRAND, where should they start?
So I would suggest starting on either on PyPy, but probably the most useful thing is just go to GitHub to the QRAND repo. Right now, I still haven't been able to put up, a read the docs website. So all the docs are in doc strings inside of the source files themselves. So you can look there. I think I put a lot of effort in making it clear. So even though it's not, in a nice format on a website, you should be, good to go with what's written in the doc string. So I would suggest going there. If you have any questions, by all means, reach out. I'm available via GitHub, and I'll try to help you out with whatever I can.
So helping set up Read the Docs might be a good onboarding project for someone who has classical dev experience. Wink, wink. Awesome.
It's also about the time. Like, it's just too many things.
Yeah, no, maintaining and doing like best practice for open source projects is a non-trivial amount of time. And that's why at the Unitary Fund we think it's pretty important to like actually pay people to do these sorts of things that actually take a lot more time than maybe they look like they do. So yeah, well, with that, I think we'll wrap up here. But thank you so much for joining me today, Pedro, and telling us about QRAND. I love random numbers. That's just going to be the soundbite. What's your favorite random number?
If I told you, I don't know if it...
Nice. Well, thank you so much, everybody in chat, for joining. I think this might be our last quantum software talk for the year, but we'll see. But yeah, always make sure to follow and subscribe here on Twitch. You'll get notifications when we go live. Also can keep on top of what we're doing on the Discord, discord.unitary.fund. I think, Pedro, you might occasionally be on there too. So, yeah, it's a great place to interact with not only Pedro, the Unitary Fund team, but the quantum open source ecosystem more broadly. So, yeah, have a great day, everybody, and we'll see you next time.
Bye. Thank you so much.